All right, this is Mole Podcast 2, and today I'm going to talk to you about relative atomic mass. Before we really get into the content here, I want to first explain, as we move into this idea of the mole, a central concept, a unit in chemistry, a unifying unit in chemistry, really. I don't want to just throw at you a bunch of definitions and show you how to do calculations. I wanted to provide a little bit of perspective as to how earlier scientists came about, even trying to understand the concept of an atom, let alone the mole. So today, in our discussion of relative atomic mass, I'm going to give you some examples and provide a little intuition and insight as to how the proof of concept of the atom came about and eventually led to the idea of a mole. Okay, so this is going to seem really obvious. When you say one object has twice the mass of another, you're expressing the mass of one relative to the other. All right, so the mass ratio of any equal number of items is going to equal the average mass ratio of the individual items. So stop and think about that for a minute. If I have 50 pennies here and 50 nickels here, and my mass ratio of those 50 items, which is equal, is the number of items are equal, rather, is a 1.5 ratio, where the nickel is 1.5 times heavier, then we can infer that an individual nickel is 1.5 times heavier on average than an individual penny. All right? And so this is John Dalton. He was an English scientist, and he, through the law of constant composition, really gave support for the concept of an atom. He bridged the gap between what we can do in lab and what we cannot see, i.e. the atom. All right, so this law basically states that a given compound will have that same mass ratio as its constituent elements. A great example would be water, okay, H2O, and go ahead and grab your periodic table out. You want to kind of have that available throughout this podcast. So H2O, there were 8 grams of oxygen for every 1 gram of hydrogen. So if you get your periodic table out and you look at the units on the bottom, the unified atomic mass units, or the mass, which I'm going to talk about in this podcast, you're going to see that there is a 16.00 for oxygen and a 1.001 for hydrogen. And so if you were to simplify that, for every one of these guys here, there would be not 16 but 8 grams. And if you're not following that totally, it's okay, because I'm going to expound on that idea throughout this podcast. But there were many other scientists involved, but John Dalton is considered the father of atomic theory for his work on constant composition and providing that proof of that concept of the atom even existed. Okay, here's an example. Let's say you wanted to find the mass of paper clips relative to thumbtacks. All right. And they're both somewhere between 1 and 2 grams, but they're really close. And so you have a scale that's accurate to a gram or so. So it would be inaccurate to weigh one of each. So why not weigh 100 paper clips, get that mass, 100 thumbtacks, get that mass, and then compare the ratios. So let's pretend you find out that the ratios of thumbtacks to paper clips for 100 individual items of each is a 1.25 grams. So in other words, thumbtacks are 1.25 grams greater in mass than the paper clips. Then you can infer from that one individual thumbtack must be 1.25 times heavier than one individual paperclip. And that's the intuition behind this whole idea that we're going to be getting into in the next couple podcasts leading into the mole. So let's go ahead and look at an example problem here. So a chemist carefully heats 0.35 grams of magnesium powder in a crucible. If you don't know what that is yet, we will be using them very soon. The magnesium reacts with atmospheric oxygen and produces 0.58 grams of magnesium oxide. So you're probably thinking, oh, cool, this is a synthesis reaction. And then I hope you're asking, is there a change in the oxidation states of the species? Is this a redox reaction as well? Okay, so what is the mass of the magnesium atom relative to the mass of the oxygen atom? So we're going to go ahead and 0.580 grams, 0 grams equals, and when you pop this in your calculator, you'll get 0.230 grams of oxygen, with this being the magnesium oxide and this being the, the magnesium itself that was put into the crucible. Okay, so we're going to get this. All right, and paying attention to sig figs, we're subtracting. We want to use our least precise. All of these have 3 sig figs and 3 significant figures beyond the decimal point as well. Notice I will always put this 0 before the decimal point. So then the way you would set this up is the mass of magnesium atoms to the mass of the oxygen atoms, all right, equals, so the mass of the magnesium, that was my 0.350 grams magnesium, and my oxygen 0.230 grams of oxygen. And when you look at that, you're going to get your answer of 1.52. 1.52. So what does that mean? That means that the magnesium is 1.52 times heavier, has 1.52 times more mass than an oxygen atom, okay? So continuing this discussion with a couple, 1 or 2 other problems we'll look at. Hydrogen was discovered to have the smallest atoms, okay? Its atoms were originally assigned an atomic mass unit of 1 U. Now, if you're looking at this, this is a relatively new unit. It's called the Unified Atomic Mass Unit. Back in the day, we would say AMU. But basically what happened is the physicists and the chemists kind of had a discussion and disagreed on what should be used. Should we be using hydrogen as a standard? Should we be using oxygen as a standard? As you'll find out, they later agreed on using carbon-12, an isotope of carbon, as the standard. But because of that, they unified their overall definition, and so that's where that's coming from. So if you look at your periodic table, you'll see 1.001 underneath the hydrogen, and 1.008, my fault, 1.0, just glancing over 8. Okay, so and the mass of all other would be expressed relative to the hydrogen. So you can see on the scale here, so oxygen, if you look at that being a 16, is 16 times heavier relative to an individual hydrogen. So again, we're talking about this idea, this concept of relative atomic mass. All right, so if the mass of the magnesium from our last example was 1.52 times the mass of the oxygen atom, and you can look at your magnesium and see what its accepted value is, and then we can actually do a computation here to figure out relative to the oxygen by simply taking the mass ratio that we found from the previous example of 1.52 and multiplying that by the mass of the oxygen. And that's going to give us a number of 24.3 unified atomic mass units. And again, you can compare that to what's on your periodic table. Really cool stuff. All right, let's do another sample problem here where we have a given mass of sodium being placed into a flask. It's reacting with chlorine gas, and 5 grams of sodium chloride are being produced. So this question here is saying, well, what is the mass of the sodium relative to the chlorine? Okay, and sodium chloride. And when you subtract these out, you're going to get 3.035 grams for the chlorine. Okay, and now we're going to set up a ratio just like we did on the last example. Mass of the sodium compared to the mass of the chlorine is equal to the 1.965 grams of sodium. Notice how I'm, labeling and making sure I have grams of chlorine, because when we get into more complex computations, you're going to see it's easy to lose track of what. So including units and identifiers throughout is good practice. And that's going to give us 0.674. That's our relative ratio, okay? So it's saying that the sodium is only 0.674. Again, notice I have those 3 digits past the decimal. Actually, for this one here, it would probably make sense to, let's see, 0.6474. I knew something was up there because I should have 4 sig figs, because both of these have 4 sig figs. So 0.6474 as massive as the chlorine. So now let's go ahead and make sure you jot that down if you haven't already. Let's go ahead and find the answer to this. So if chlorine has an atomic mass of 35.5 atomic mass units, then what is the atomic mass of sodium? So what we're going to do is we're going to take our number here, 0.6474, and multiply it by the mass, 35.5 U, and that is going to give us an answer of 23.0 U, and that would be the atomic mass of the sodium. Okay, so gives you a good idea here of how scientists began to come up with these concepts to again bridge tangible what we can do in lab and what we cannot see, providing this proof of the mole and of the atom. Okay, so our Georgia Standards of Excellence today are dealing with this these concepts of the mole, Avogadro's number, and how to not only conceptualize but also calculate a number of different items here. So that's going to conclude everything I need to talk to you about today. I'll see you in class. Thank you.